Hello class. So today what we'll be going through is ordinary differential equations. So ordinary differential equations are the most basic form of a continuous dynamical system, right? So the dynamical systems that we were looking at before had steps like un plus 1, un plus 2. And so those are called discrete dynamical systems because the time on which they work is a discrete space, right? They step every integer. When we get to ordinary differential equations, the time is now going to become something that is continuous. These models have very different properties, right? So for example, if your derivative at 1 is positive, then it will always be positive. And so therefore, if you ever get to the value of 1, you can never go below it, right? Because you're always going to be increasing if it's a one-dimensional model. So if you have arrows pointing up, you're going to go up. You have arrows pointing down, you're going to go down. That's different from a discrete model, right? Because in a discrete model, you could have something like where you jump over a region where, maybe you're going up, 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 but then you jump over something that brings you to go down, 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 right? In continuous models, that can't happen, right? Because you can't jump over anything. Time is there's an infinitesimal step where you'll hit the boundary point where the behaviors change, right? So the discrete dynamical systems have a very different property from their continuous counterparts, and that property is actually very crucial to understand how to discretize and computationally evaluate ordinary differential equations, right? Because you want to get the continuous properties correct, right? Otherwise, you're getting the actual model and its simulation incorrect. But everything that you do on a computer has to be discretized. So whenever we look at a simulation of an ordinary differential equation, what we're actually looking at is the output of a discrete dynamical system, which we hope has the same properties as a continuous dynamical system. And that's really the goal of what we'll be looking at in this lecture. How do you construct discrete dynamical systems that will have these properties to match the continuous counterparts? So we have a sense of parallelism, right? We understand how we can do fast code of serial code and parallelize over the parameters of a system. Now let's move to this continuous case, which can be a lot more computationally intensive and have a lot more features or a much bigger space of methods to explore. So why do continuous dynamical systems come up? Well, because many physical systems themselves are not discrete, right? They are at least approximately, for anything that is orders of magnitude above Planck scale, they are something that is pretty continuous. So for example, when you look at time, time seems to be continuous. If you can take half of time, quarter of time, you can ask a question of, if you're to throw a ball at 0.1238625 seconds from the throw, where is the ball, right? That is a valid question. And so therefore you need to have dynamical systems that can analyze that behavior. But the other thing is that, continuous behavior, as I mentioned, can be fundamental to the way that the dynamics of physical objects work. So for example, when you throw a ball at the wall, it might hit the wall at 2.0259823 seconds, right? If you don't treat the system continuously, then at 2 seconds you're in front of the wall, at 3 seconds you're behind the wall, right? So you need to have this ability to be able to say, this is the time point when it hit the wall. When it hits the wall, this dynamic has a change. And this is all in the language of ordinary differential equations and hybrid dynamical systems when you start to have events involved. We'll go into more advanced versions of differential equations in future lectures. This lecture is going to be solely on the very basic continuous ordinary differential equation. So what is an ordinary differential equation? Just to make sure everyone is on the same footing, right? So an ordinary differential equation is a relationship that is defined by a derivative. And so the general form is u prime equals f of upt, where u is state values, p are the parameters, and t is the time, or the independent variable. The states also are known as the dependent variable because their value is dependent on the independent variable. So here we would write u as an equation u of t. And just like we discussed with the discrete dynamical systems, you can have vector forms of this as well. So u prime, u can be a vector. Prime would mean the derivative of every single component. So let me write this down. 1 second here. So the derivative of every single component would be, right, so the vector form of u prime equals f of upt. This can also be written as, u1 prime equals f1 of u1, this vector u1, u2, u3, pt, u2 prime equals, the same thing except f2. And you can get the point for what u3 prime would be, right? So u3 prime equals f3, right? So the way that we write this is just as a vector notation, where we say that u equals u1, u2, u3, and then what we mean by the notation u prime on a vector is simply that this is just u1 prime, u2 prime, u3 prime, right? So anytime that we're talking about the dynamical systems, we should always think about the fact that we have multiple variables, right? These state variables are usually, for example, in a physical system, you have the position and velocity, right? So u1 is position, u2 is velocity. How does both these states of the system evolve over time? Let's actually write that down as a let's actually do a simple exercise to understand how to write down some systems of ordinary differential equations. Now, this form might not seem as universal at first, but I mean, just like what we saw with the discrete ordinary differential or the discrete dynamical system, you can find many ways to be able to transform these other forms, like delayed systems and like delayed systems into multidimensional versions of the standard form, right? So in an ordinary differential equation here, let's look at one way to be able to transform some other common ordinary differential equations to a system of first order differential equations. So let's say we have the system u prime prime equals minus kx. Right, so this is the second order ordinary differential equation, which we were looking at before, which is, if I was to put an m here, right, this is that this is that the m times a, right? So this is the acceleration term. It's the second derivative. So this is f equals ma. It's a second order ordinary differential equation. I claim that this equation is can be written as one of these types of u prime equals f upt. So how would you do that? Well, what we can do is we can say that the velocity is just the first derivative of the of u, right? So we actually have, this should be u, right? So this is the spring equation with Hooke's law. And so what we can do is we can say, well, u prime equals v. This is the velocity, right? And so if we let u prime equal v, then what is v prime going to be? Well, v prime equals u. This is u prime, right? Which is the same as u double prime, which is equal to minus ku over m, right? And so there we go. We have a system of ordinary differential equations, all in first order, because we now have u prime equals v and v prime equals minus ku over m. And so this is a system of two ordinary differential equations captured the second order equation, right? it's just written in a slightly different way, but this shows that you can transform a lot of these different types of equations into this specific form. So in some sense, this is a very common form to find in physical equations. So now, in the simplest sense, right, if you want to solve an ordinary differential equation, what are you doing? Well, you take the integral of both sides. Right? So the integral of the left side, it's u prime. Take the integral with respect to t. U prime of t dt, well, that's the antiderivative, right? So that becomes u. And now the other side, it's the integral of f of upt dt. And how come this is a difficult equation to solve? Well, you're searching for u, but u also shows up in this possibly nonlinear function. And so this means that this is an integral in some sense, right? It is an integral. The solution to an ordinary differential equation is an integral, but it's an implicit integral, right? Because the solution of, the integral for this ordinary differential equation is partially defined by its own solution. And this makes sense, right? Because as you go along the equations, right, as you evolve a system, your system is dependent on your current state, which, it's dependent on slightly in the past. And so you always need to know where you are to know where you're going forward, right? And so this implicit behavior is what really differentiates it from simple quadrature. So the problem with trying to understand the behavior of ordinary differential equations really comes from the fact that almost none of these equations have an analytical solution. And that makes sense because implicit equations themselves they rarely have an analytical solution. That's why they're left implicit. And so something that is implicitly defined by an integral is itself just an order of magnitude harder. Many integrals don't have analytical solutions. The classic one is that the integral of e to the minus x squared, the Gaussian distribution, does not have a definite integral that you can write down, right? So you can define it as the earth function, but you cannot write that down in terms of elementary functions. And so even very simple cases of this do not have analytical solutions. And so this is a very common case where, since a lot of physics is ordinary differential equations, people heavily make use of simulation to be able to understand how these systems evolve. And so here what I want to start with is just how do you simulate these systems in Julia. I want to showcase a little bit of differential equations.jl, which we could pull in by using differential equations. I will note that differential equations is quite a huge library. You don't necessarily need to use all of differential equations for all of your use cases because differential equations encapsulates many of these other types of equations. So one trick that a lot of people like to make use of, which is documented in here in the low dependency usage part of the documentation, is you don't generally need to use all the differential equations. It's a nice, easy thing to write down. But if you want to decrease your load time or be more specific in what you're using, you can directly go to some of these solver libraries. So for example, ordinary diffeq.jl is a solver library that provides the ODE solvers that are written in pure Julia. We can, so there's some examples in here of how to use the lower dependency usage. I'm just going to write using differential equations to keep everything simple. But if you're, for example, developing a library based off of this, you might want to directly use ordinary diffeq, stochastic diffeq, sundials, or one of these component libraries. So let's take a look at defining an ordinary differential equation. If we were to look at the Lorenz equations, right, we would see this as something where it's u prime equals f of upt, where f is defined as, right, one of these equations where you have u prime 1 equals f1 of upt, u prime 2 equals f2. And so what we want to do is we want to write this down in terms of vector notation. So for that we do, so we want to use an in-place function because remember, we want to use a form that is not going to be allocating memory all the time. In differential equations, it allows you to use both an in-place and out-of-place form, But you should choose the one that is more efficient for your use case. So if you're going to be writing code on vectors, of course, you do not want to be allocating new vectors every single time you have a function call. And so therefore we use the in-place version. So here we define that the derivative of the first function, right, in place, is equal to, well, we use u2 minus u1, and we have parameter 1 here. We have u1, u2, or u3 and u2. And so, as you go through the code, you can just see that u1 equals x, u3 equals z, and u2 equals y. And so if you go through this is how you write down dx, dy, dz in terms of the three components, right? So, quick question for the class. How can you speed this up a little? Think about it for a second. Ding, ding, ding. Yes, so one of the ways that you can actually speed up this code more than what I've shown here is you can make use of static arrays, right? Remember that you can use in-place forms with static arrays if your systems are sufficiently small. 3 is definitely sufficiently small enough to accelerate this with static arrays. So if you want to, you can try doing this on your own, where you define the system using static arrays to output static arrays, and you can do this a bit faster than what I'm showing here. But I'm just going to show the array version because it's probably the most standard. Ordinary differential equations, in a lot of cases, get larger than static arrays, so this is probably a good version to know. So next we give the initial condition, right? Because in order to solve such an equation, u prime equals f of upt, you need to know what happens at t0 because the evolution is dependent on your current state. So you need to know the current state at the start to start moving things forward to then get to the final state. So here I'm going to say that the start, I'm going to have x equals 1, y equals 0, z equals 0. Right, notice the types that I used for defining the initial conditions here, right? I'm saying make u0 be an array of float 64s and then evolve a system with arrays of float 64. I can actually change that depending on how I want to solve the system. And I'll be showcasing a little bit of that in a second, right? So let me actually put this over to the side here, so that way I'm kind of following along. Right, so I define the Lorenz equation, I define my u0, I define my time span. So my time span tells the system, over what time span am I going to be doing the evolution of the system. So I want to evolve it from 0 to 100. I want my parameters, right? Remember, p1 equals sigma, p2 equals rho, and p3 equals beta. I want my sigma, rho, beta to be equal to these values. And then I want to define an ODE, which has this right-hand side function, this initial condition, this time span, and these parameters. Right? And now I can just solve it by saying solve the problem, and then let me grab the plot library and say plot the problem. Right? So while the plot library is going to be loading here, let me describe what the solution is going to look like, right? So the solution of this is going to be, well, it's this like funky little system here, right? Where you have one portion which is moving along, and then suddenly it's able to swap to, or it's able to kind of, this one is able to swap between two kind of values, right? It's kind of hard to understand what's going on. You plot the system variables x, y, z over time. So let's actually plot them as x, y, z itself. And what you see is the classic butterfly wing, right? So this is actually known as the Lorenz attractor. It's a very well-known infamous equation because this is one of the equations from which chaos was first discovered. So one of the interesting things about this equation is that very small differences in the input cause very large differences in the output, and we'll explore that in a second, right? So what I did here to be able to do this kind of plot was I did bars equals 1, 2, 3, which basically just says the first dimension should be plotted as x, the second dimension should be plotted as y, second dimension should be plotted as z. Right, so let me show that here. So vars equals 1, 2, 3. and boom, we should get the same plot, right? Now, what happens if you want to plot with time? Well, time is a sentinel for 0. So let's plot with time. And here you can see that we have a time axis and we have an x and z, or x and y and z. So one of the interesting things about this plot, which you should notice almost right away, is it looks fairly smooth, right? It looks fairly nice. And if I turn off a certain setting here, so dense plot equals false, we see that that nicety goes away. Let me plot it in the phase space. Right, so when we talk about an ordinary differential equation, phase space is the space of these states, right? How the states evolve together. So when I plot this in phase space, what we see is that we lose a lot of that nice behavior, right? It doesn't look so round anymore. And the reason is because a solution to a differential equation, right, remember, is a continuous object, while its computational solution is a discrete object. So if we actually look into the solution object, we'll find that there is a t vector, which is all the t's that it chose to step to, which is, discrete values of t, which have discrete values of u. It turns out that there are ways to make these discrete objects into continuous objects by using interpolations. So you can turn this into a function of time, right? And this function of time is then what is used to make this nice plot. So we can actually overlay the two together if you want to kind of see. Yeah, so I can do a plot of the continuous version, and then I can do a scatter plot of the points of the solution on top of it. And you can see all the different points that it chose to step to, and how it's automatically using this continuous interpolation for generating the nicer plot on top, right? So that's one neat thing about, differential equation solvers, or what they could have. This is called a dense output. Because the solution is actually continuous, you might want to be able to represent the continuous solution instead of just the discrete solution, right? So that tells you that there's some kind of mathematics going on in the background for how do you resolve how these curves are forming. Some other details about using the differential equation solver library that you should be aware of. You are going to make use of it in some of the homework problems, and most of the information that you'll need should come from the differential equation solver library itself. In the documentation, you can find this first tutorial. This first tutorial explains most of the details about using the library, such as, for example, you can directly choose what kind of method you want to use by saying, here I want to use the sit5 method, and we'll go over to the differences in ODE solver methods. Well, that's today, right? So today and the next few lectures. So you can choose different methods. You can act upon the solution as though it was an array to grab the explicit values. So sol of 5 is the value at sol.t of 5, right? The sol.t at this point in time, you had a given value for the solution, and you can grab these arrays. You can convert this into an actual matrix, for example, and then directly work on the matrix, whatever you feel comfortable with. And so the documentation will go through all of those kinds of aspects, and pay attention to, for example, the aspects that have to deal with saving. So for example, since this is a continuous object, if you want specific discrete objects out, you have to ask for it. So for example, if you want to save at every 0.1 time steps, you can say save at 0.1, and then you'll save 1,000 points, where these 1,000 points are evenly spaced by 0.1, right? Does this mean that it takes a dt of 0.1? No, it doesn't mean that it's actually stepping 0.1, right? Because remember, we have this continuous object, and so what we can do is we can use the continuous object to be able to give us outputs at any point in time. And so the points that you're saving at are not necessarily the same as the DTs for an actual differential equation solver that's used in a library or in production, right? And we'll go over some of the continuous aspects that allow this to occur. But this is just kind of a detail to be aware of. This is very different from choosing delta t to be equal 0.1. And the reason is because, choosing given delta t's has specific, ramifications in terms of error. So if we want to do something like, I want to solve this with rel_tol equals 1e minus 8, you can change the relative tolerance and increase the number of steps that are required to do the solution without having to change the actual amount of spaces where you're actually saving the output. These two ideas are different. Where you save output is not necessarily the same as where you are stepping to. This is similar actually, but what we looked at with the discrete dynamical system before, right, where we were thinking about how can you save allocations if you're having to save so much of the time series. Well, here you're having to save small bits of the time series as you move along. Every once in a while you have to generate a save. This is kind of that same idea where how you're stepping can be disconnected from the way that you're doing the saving, and so your caching and ideas between them need to be different. We'll mention more about this. But so the differential equation solver documentation at diffeq.iml.ai will describe everything that you need to know for the problem sets and such. So I'll leave the rest to there. So where do differential equations come up? Well, one major place where differential equations kind of were born was for n-body problems in astronomy, right? The classic Newton problems. And once again, this comes from the idea that F equals ma, right? That's the classic Newton law. And if F equals ma and you know an equation between all the different planets or all the different stars or all the different objects that you're trying to look at the gravitational or electrical force for, right, then you have an equation for how things are changing and what that force is between the things. And so by using that trick, which I mentioned, right, so x prime equals velocity prime is the acceleration, you can write down entire sets of equations for how n bodies evolve. So one interesting example for this is the Pleiades problem, which is a 7-star chaotic system. So you can write down the equation for the stars is really just you write down, well, each of the stars have a gravitational pull to each other, and so all you need to know is the mass of each of the stars and their initial velocities and their initial positions, right? If you have those three quantities for each star, then you can write down this equation where you say, well, here I'm going to make my vector be right, my vector of points now, right? So I'm going to look at this 3-body problem in 2 dimensions. So for each planet, I have an x, I have a y, I have an x prime, and I have a y prime, right? So I'm going to make the first part of my vector be all the x's, and make the second part of my vector be all the y's. The third part of my vector is all the x primes, and the fourth part of my vector is all the w's, right? So this is using a view, so that way these are all non-allocating, just pointing to the same memory as before. And now the first set of equations I want to do is that x prime equals v and y prime equals w, right? So there we go. There we are, just mutating the x prime term and the y prime term to match the derivative. Now the next thing I want to do is I want to evaluate Newton's laws between all of these given bodies, right? So what you first have to do is you have to calculate what the radius is, right, which is the Euclidean distance between the different planets. And then from that, then you do, well, then you just do Newton's law, where you then, I guess we're doing an approximation to the masses here, where we're assuming that all the masses are the same. And there you go. Then you have a version of Newton's law. Actually, I think that we're doing an approximation where the masses are the values j. But yeah, it's derived from the n-body problem. And this is then a way to write down this is a classic ODE that's used in ODE solver benchmark, where there's this list of, these are the initial x's and y's, which people generally use, which are taken from the actual physical system. And now, yeah, so this is where we assume mi equals I, and that's why j shows up here. So the masses are equal to the ith object, which is supposed to be a good approximation for the system. And so if we plot it, we see, well, this is a nice star system, and sorry for the cut there. I noticed that I did have a small error in the first version of the lecture notes, and they'll be updated. Essentially, I had an extra 0 in here. So this is the solution to the Pleiades problem, where it's a seven planet or 7-star system with a quasi collision. So everything kind of moves forwards until everything has a collision, and then things start to spiral out of control. So if we look at this in phase space, it's much easier to see that there are systems that come in, and then they all kind of do a loop-de-loop, and then some of them start to spiral out. Let me do another plot here in terms of t-span equals 0.0 to 2.0, and then it might be easier to see how everything starts nearby. There's this kind of quasi-collision and kind of throws everything out of balance, and then you have some of these stars start to fly outwards, and then these two actually make a very fun result, because you can see that they kind of do that spirally behavior. So yeah, so I mean, this is an example you can kind of sit down and look at for a while. But yeah, so this is one example, right? So n-body problems, like molecular dynamics, stars and galaxies, Newton's laws, Einstein's gravitational laws, all of these form differential equations, ordinary differential. Some of them form partial differential equations, but partial differential equations, when you discretize them, we'll actually see that what you get are ordinary differential equations. So at the end of the day, a lot of things in physics are solving ordinary differential equations. So another case which shows up quite often is population ecology. So population ecology measures how different populations or different organization species evolve over time. So this, for example, is the Lockwood-Volterra model. It's a very common model for predator and prey, which is simply that you have an equation where the amount of rabbits increases exponentially, because on its own, if you let the rabbit population do its thing, it just grows. But then you have that it decreases, right? So minus with respect to the other guys, which are the wolves, right? So the wolves eat the rabbits. So this decreases the rabbit population. How do you get more rabbit, or how do you get more wolves? Well, when there's more rabbits, there's more food, so you get more wolves. And conversely, you just say, well, wolves, they don't have a natural predator, and so they'll exponentially die off. So you have rabbits and wolves, and then this gives you this cyclic dynamics. So this is actually a very interesting phenomenon that can happen in both discrete and continuous dynamical systems. You can just kind of say this is the interaction that will occur, and the output can have emergent behavior, right? So this is an emergent behavior where you have cyclic solutions, right? Nothing about this equation specifically says it should be a cyclic solution. It's just if you numerically solve this equation, you see that those laws together give you a cyclic solution. And so that would mean that, in this case, this is one of the reasons why people expect that predator and prey solutions or predator-prey relationships will have kind of, cyclic or seasonal behavior. Another case which is very common for ordinary differential equation modeling is biochemistry. Right, so in biochemistry, all of your equations are given by chemical kinetics equations. Chemical kinetic equations are the concentration of X changes over time, like, Y. And so all of those equations are themselves ordinary differential equations. Now, the really interesting thing about these biochemical equations is that they tend to have very large order of magnitude time differences between the different equations. So one way that manifests itself is that it means that when you have the parameters in these kinds of models, it means that they can be large orders of magnitude apart. So for example, you can have one chemical that is catalyzing the other, causing reactions on the speed of 3 to the 7th, per second or so. While in other cases, you can have uncatalyzed reactions, which are 9 orders of magnitude separated in time. This has a phenomena that we call stiffness, We'll see it manifest as a fast-slow system where you have a fast manifold and a slow manifold. So if we just plot it in normal time, solving the equation from 0 to 10,000, we see that there is a very, there's a very pronounced one thing goes up while the other thing goes down over the long time scale, right? But that doesn't actually capture what's going on, right? There's almost, you see almost nothing with the second species, so you might think that it has no effect. But if you actually kind of zoom in here, well, not zoom in, but actually plot it in log scale, right? In log scale, what we see is that the second term goes up and then goes down in something that is in about 1 second, right? So in 1 second, it goes up, and that starts to catalyze the reaction, and it goes down, and then from there, the reaction takes on itself. How does that occur? Well, the way that you can see that this occurs is that you have the second variable show up. So y2 shows up in this second equation. So when you have more y1, you get y2, and then from y2 you get it very quickly, right? This is the quickest reaction. It very quickly causes itself to turn into y3. So y2 is this intermediate, right? You have this reaction where it goes from y1 to y2 to y3, but you have this catalyzing portion, whereas you get more y3, then you more quickly get down to y2, or as you get more y3, then you more quickly decrease in y2. So very quickly, you have this intermediate state, which goes up and it starts the reaction. But once you start to get enough y3, then it tends to push down y2 again, and so you tend to not see as much y2, but it's still required in order to start this reaction. Right, so this is what we see as a transient phenomena, right? You need this small portion to be able to activate in order to have this switch from 1 to 3, even though it's on the time span of 1 second. That 1 second is actually what causes that solution to look like this over 10,000 seconds. Okay, so this is a fast slow system that has stiff behavior, and we'll see why this manifests as one of the canonical stiff equations. So other chemical reactions are really one of the core ways that you get stiff equations. So they're very interesting to ordinary differential equations literature, and also because biology has seen a major boom. Computational biology has been a major subject in the last 20-30 years. There's been a lot that's been done in ordinary differential equation modeling for understanding these systems. So in another case where this shows up is chemical physics, where you can begin to write down, these reactions between all of the different pollutants. Here's a canonical model for that, where once again you have a bunch of reaction rates which can be differing on 8 to 9 orders of magnitude that describe how different chemical concentrations are reacting. Each of these are one of your reactant equations, like if you were to write down the chemical kinetics, like Chemistry 101. And then you just describe the way that the physics, the chemical reactions are occurring, what they're causing. When you add this all together, this gives you your chemical kinetic system, and then you simulate it. And sometimes it can look like there's little behavior going on, but remember that in these small little portions of time, there are some extreme transient behavior that's occurring. So these are some of the phenomena that we want to understand. And these are some phenomena that are very hard to capture with discrete dynamical systems. We'll actually see that causes some of the numerical difficulties in the equations, right? Because if you want to look at the time scale to understand this behavior, right, that is at a very, very small size. Like you're talking about microseconds to understand how some of this fast behavior is occurring, right? You want to do a microsecond step for the discrete system if you want to understand this behavior over from 0 to 10 to the 0th, right? But from 10 to the 0 to 10 to the 5th, you don't want to do it as a microseconds, right? It will take you years to finish that simulation if you did that. And so you want to use different time spans or to represent different parts of the equation, and you want to really have all this work in unison. And it's really only well described in the actual continuous framework. Okay, so ordinary differential equations and the continuous models that they represent is actually not just, it's not just an abstraction over the discrete models, it is actually a